All right, time for another draftphysics.com, debatephysics.com also. But you just can't get anybody to engage in a debate, an argument, a back and forth regarding the credibility of the idea, the ideas, the axioms of physics, which are that some sort of bent thing, okay, is causing gravity, which in turn causes a bunch of action, energy, momentum, pressure, and heat. And then somehow they talk about conservation, and yet they have a source of energy with no mechanism to circularly put it back into the cause of the effect. So you have too much effect and no way to put it back into cause, kind of thing. And then they have wave particle duality, which is just silly on its face. And it's clearly an explicit, definable mechanism. It's not doing two different things. It has to be rationally consistent and doing one thing all the time, which is particling, by the way. And it's easy to understand. Prove, even. Using the double slit experiment as a nail in the coffin evidence, that it's a particle, not a wave. And then the kinetic energy formula, which, Super Dave is going to talk about in this video, and use these terms, scalar and vector. And so they actually teach this, and nobody laughs, but that speed doesn't have a direction. So somehow you can have a speed and it's not in a direction. Yeah, it's just, who knows where it is? It's an unknown velocity without a direction. You're moving really fast, but you're not moving in a direction. That's what they think. That's how they think the physical universe works, that you can have some sort of speed, okay, but it doesn't have a direction. And then if you use the word velocity, that means it does have a direction. So if you talk about its speed, you're talking about some unknown movement in an unknown direction. Okay, it's just too silly, right? And so they teach this to kids, which, is child abuse, but whatever. Everybody gets away with that now. The whole world is just, oh, God, it really is idiocracy. We really, it's, movies aren't imitating life. Life is imitating the movies. All you can do is that shake your head thing. What the fuck? What planet is this? I mean, god damn. Fucked up is what it is. Planet of the fucked in the heads. Alright, so anyway, let's play the video and see where this goes. Very bad anyway is where it's going to go. So I'm just playing them in series. So he has them in a playlist. This is how they teach their physics. So, we did the, oh, gee, they had some ideas in the past, and now we have ideas in the future, and, our ideas are better than their ideas, but we still use their ideas. And continuing.
Professor Dave here. Let's talk about scalars and vectors.
He knows a lot about the science stuff. Professor Dave explains.
Physics is all about some pretty amazing...
So he's using this old archaic image that they don't believe it is, but they do believe it's doing this swirly stuff. They think electrons are constantly orbiting the nucleus in some way. We just can't see them. We can't identify them as having a real position because they're in some superposition of all positions. I mean, they teach this, like, you're supposed to take it seriously. And how do they know this? Yeah, they don't know this. They just made it up. Okay, now I would argue that the the entire thing is a magnetic thing. It's the monopoles of magnetism are the electron and the proton. And you can arrange north and south magnets in such a way as they stick in positions because they can't go anywhere else. So I guess I could draw that real quick. No, I don't know how quick it'll be, but I could try it just for fun. Where were we? Yeah, I gotta get rid of this. It's been a while. So which one do I have to get rid of? I have to get rid of, what the hell is that thing called? This, I believe. That's it. Oh, that's unfortunate. We got a bit of a halo in there. Anyway, so the simple argument would be is you have the nucleus, which, see, they say a proton and a, they say there's electrons, protons, and neutrons, and they won't concede, even though it decays, okay, into a, you know, a neutron decays into an electron and a proton, and something they call an anti-neutrino. Now, why you would even believe this thing exists, right? It'd be just like a little nothing dot, because it goes right through the Earth. It's so nothing. But this is what it comes out when you leave neutrons alone. This is what they turn into, is an electron and a proton. I could separate them in distance. And obviously when they're connected to each other, when they're under pressure, well, they don't even have to be under pressure, because you can understand why electrons would stick to protons. It makes perfectly good sense. It's obeying Maxwell's laws. Maxwell's law basically says, yeah, you put an electron and a proton in a box, they will, you know, they'll do this intimate thing. So anyway, so this is really what a neutron is. It's not a neutral particle. It's a particle that has both poles. And so, yeah, if it's spinning, you could certainly understand how it would look. Say if the positive was blue and red, and the negative was blue, you could understand that if you spun it, it would look purple. No. So it would look neutral, but not neutral. Not really. It's the first dipole, and this is what the sun is making. So the sun is basically under pressure, right? The pressure from the external world. And what it's basically doing is forcing everything to get into these relationships where you have a proton and then a neutron. Say this is the this is the electron. No, we'll call the light ones protons. And you could understand they can be in a relationship to each other, okay, where they're going to stick to each other, but they can't have, protons can't be too close to protons, electrons can't be too close to electrons. So you can draw some sort of pattern, like a helium nucleus, some kind of geometry, where you have what's necessary, which is in the nucleus you're going to have twice as many protons as you have electrons. And, it's not that hard to make the arrangement. I've done it in previous videos, where that works. You could just understand it. If I put an electron down here, you could understand that protons could line up over here and here and here and here and here and here. They can be in the 3 dimensions. I really can't move this over, so you'll just have to imagine you saw the rest of that drawing. Yes, I can't move this. I'll figure it out eventually, get this right. All right, so the idea of it being magnetic works. I'm not sure if I can erase it without making too much of a mess. It probably needs the aid of some kind of liquid medium, but whatever. All right, so if you have the net positive nucleus, but you could understand that the nucleus also has electrons in it, so it's, let's just put 3 electrons in here. So there's certain places, from certain points of view, the nucleus would look negative. From other points of view, it would look very positive. And the idea is the electrons, okay, the orbiting electrons. So you have a 2-to-1 relationship in here of protons, so it's a net positive. Okay, it's more positive than negative. And the remaining balancing electrons are out here. And you can understand that they would be in positions, okay, where they would be seeing the protons, okay, so they would be connecting to places where they're as far away from electrons as possible and as close to a proton as possible. And so you can see the geometry, and there's no need for orbits, because you can understand that this electron can't really get close to this proton without getting closer to these electrons. So the repelling force from the electrons will prevent this electron from crashing into the nucleus. So even though the nucleus is net positive, It's not positive completely, and therefore the electron can't just crash into it, because it's still going to end up getting too close to too many electrons, and the two forces will end up balancing each other. The attraction to the proton will balance the repulsion from the two electrons that are a little further away. And that geometric magnetic model works just fine. So instead of there, okay, you saw it before, but instead of that thing, okay, yeah, no, it could be magnetic. They don't even consider it. They won't even talk about it. They won't even speculate about it, because they decided on their, their God, Jesus, the Holy Ghost thing. They have their own, they've already established the players in their religion, and they won't negotiate regarding how credible a theory that is, and such.
Amazing stuff, from subatomic particles to everything you see in space.
Yes, and it all should be something. There's no, it should be like evolution. You kind of understand it's made out of simpler and simpler and smaller things, and that there's not properties. Small things really can't have properties that are more sophisticated and elaborate than the thing they're going to make, the puzzle they're going to make. The pieces can't be more complicated. The pixel can't be more complicated than the image you can make out of pixels, that kind of thing.
But before we dive into all that, just as with any other science, we have to get a few things out of the way in terms of language and convention.
So whatever that even means. So this is just establishing the dogma. Okay, so if you're going to be a pepper, like him, you have to believe this kind of nonsense, this gibberish, the catechism. Okay. So this is, whatever he says, is this is science. What science really is proving things, evidence, facts, establishing facts, and then building, putting fact A plus fact B equals fact C. But somewhere in there, there's supposed to be some way you prove things instead of just assert them. And their physics just asserts. It doesn't prove.
To learn about science, we have to know how people do science and how science is communicated.
So science isn't necessarily everything done that has a lab coat. Some people are doing things that aren't really science. Okay, they're just making nylon or something. They're just blacksmithing. It's not really science. The science is the underlying understanding that might lead you to do it the right way. Now, if all you're doing is imitating what somebody taught you, you're not really doing science. Science is building and proving, as stated. It's not making money.
So we must first know about things like the units of measurement that the scientific community uses.
So those units are a squared second, whatever the hell that would be. Yeah. All right. So he jumped through this pretty quick. The average atom, I thought the average atom was actually 0.5 times 10. Yeah, I mean, that's what I saw. So it depends on who you ask, I guess. But whatever. I mean, it comes out to something like it's like an atom is 0.5 nanometers. It's a 5, not a 1. That's the point. But anyway, continuing.
Notation, which is used to report very small and very large numbers that will be common in physics, and dimensional analysis for converting between.
So whatever, that's just a manipulate the formula to confuse is what a lot of this comes down to. So as I gave the example in the Newtonian formula of where you take G and then you do it times m1 times m2 divided by r squared, you could just rewrite that as G times m1 divided by r squared plus G times m2. And then you would understand that the two gravities are completely distinct. The Earth creates its own, the Moon, for example, creates its own, and there's really no point in mathematically combining them if, to confuse that somehow the Moon has to be there for Earth to have its gravitational field, and it doesn't. So they're not interlocked in some way, and that their math implies that you need both elements, when clearly, no, you just need one element, one mass, and the same equation holds, and you don't bother with the times the other mass. You don't need M2, and M2 doesn't need M1. But that's what this leads to, is creating, versions of the same thing that look different, because somehow how they look does matter to people, and how they're impressed and how they remember them.
Between units. Luckily, we have already gone over these in my chemistry series, but in case you missed those tutorials, you may want to check them out at some point. Beyond these basics, one other...
So there was no basic there, okay? It just says that, okay, we're going to measure length in meters, we're going to measure weight in kilograms, but this really just should be grams, and then we're going to measure velocity, that's the meters, per second. Per second.
Prerequisite for studying physics is the understanding of scalars and vectors.
So there's nothing to understand except these are just made-up concepts, that somehow there's some energy in the universe that you can't understand it as being completely identifiable as motion in a direction. And yes, I could blow up a piece of dynamite and it's going to have motion in all directions. But each part of the explosion is clearly a piece of the explosion. You could take a pipe bomb and paint each piece a different color, and then you could explode the bomb and you could see that, all the different pieces actually went to a different location. Yeah, so what? Each individual piece had a very straight line vector.
To put it briefly, a scalar is a quantity that communicates a particular size or magnitude.
So there's no confusion in the basic idea of mass, okay, and then velocity. And there's no reason to pretend, well, we already know those are numbers, and they get bigger and bigger as you're going faster and faster, and you're getting bigger and bigger as you're getting heavier. So what's the there's no complication there. We don't, it's not confusing without these concepts. So without this weird distinction that we're going to have some separate idea that half the physics goes scalar and half the physics goes vector. It's all vector. There's no way to move in the universe without moving in a line. It's the nature of movement. Yeah. It really is. I mean, their own math demonstrates it. I mean, you shoot a cannonball off the top of a mountain, right? Fast enough. And gravity's pushing it down, right? So if you go fast enough, faster than the gravity can push it down, blah, 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 you put it in orbit.
These can be things like the mass of a book, the amount of time you spend watching this clip.
So all of these things are going to have a magnitude no matter what. There's no way that they can't. It's just you're raising or lowering temperature. Your time ticks. You can't go backwards. And things weigh, and you can weigh twice as much. You can weigh 3 times as much. What does scalar have to do with it? Why do I need this word scalar? It's a magnitude, and there's no point in having 2 words to describe magnitude, scalar and vector. The argument is there's one conceptually rational way to understand them. They are all vectors.
Or the temperature outside today. These are numerical quantities, along with any relevant units that simply answer the question, how much?
Yeah, so how much? What do I need to? Why do I need to call that scalaring? Yeah, there's no reason at all. Magnitude covers it. Why do I need the word scalar to qualify the word magnitude? I don't need the word scalar. It doesn't serve any purpose. They invented this in the 1800s to justify the fact that they had momentum and kinetic energy, two completely different theories of energy. And the only way they could resolve it was to play this word game and pretend that kinetic energy is some sort of scalar energy that just has a magnitude, but it doesn't have a direction. So where they had to make up fake notions.
A vector is different because a vector has not only magnitude, but also...
Yeah, everything is going to have that. There's no way you have speed without direction. So again, they're just playing silly, idiotic word games. I mean, they're such obvious word games. They're such obvious evasions of the truth. You just don't need this. It's just, so again, they have a magnitude duality. We have magnitude scalar, we have magnitude vector. And it just doesn't mean anything because nothing has a magnitude in any other way than motion. That's the energy.
Direction. So it answers both how much and which way. Vectors will...
So again, there's no way to avoid which way. I mean, there's no way to say it has speed and we don't know which way.
Be very important in physics because when we look at forces, we want to know how much force is being applied.
Right. He's talking like such a fucking douche here. Anyway, well, that fits. But anyway, how much force is applied? It's just such, Anyway, so what's the argument is that you have two ways to find out. Just do the mv thing or the mv squared thing. That's the definition of force. So Newton clearly said force equals momentum. He said it pretty damn clearly. There's no way to evade it. And if you want to know the net force, you don't have to worry about time because obviously it's a net amount. You don't care how long it took for the net amount to happen. You're just saying what is the net change. And he clearly stated twice the velocity, twice the force, 3 times the velocity, 3 times the force. This guy's arguing Newton was wrong, and he's certainly not doing it very well. This is not going to prove Newton wrong.
But also in which direction. These forces will always be represented by vectors, where the direction the arrow is pointing is important information.
So, of course, it's important information, but there's no way for you to draw speed. So show me what speed looks like. Show me how you draw speed without using a vector. Oh, that's right, you can't do it.
Just as much as the length of the arrow, which will indicate the magnitude of the vector. To denote vectors, we usually use letters in bold font with an arrow on top. As we learn more about physics...
And if it doesn't have an arrow, that means we don't know which direction it's going in, so it doesn't have a direction. That's the notion, that somehow not knowing its direction means that its direction can be squared. We have twice as much or 10 times as much energy somehow.
We will use vectors to predict the motion of objects. And if there are several forces acting on an object, as there often are...
So again, there's not force. This is where, again, you could just make a simple argument. So I'll make the simple argument. I mean, they're just screwing this up so badly. I mean, it's just so obviously wrong to call friction a force. Friction isn't a force. So let's do that. Have to erase again. All right. So the simplest argument, you're just saying, look, when something is applying friction, so let's say I just drop something, so it's going to increase its velocity, blah, 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 blah. Now there's no, well, what the hell happened there? All right. Camera got tilted or something? I don't know. All right. Up and down should be up and down, and it's not. Anyway, so this could drop. And it's, if I keep it a millimeter from the surface, it won't mean anything. It won't transfer any energy. It won't lose any energy. There won't be any friction. Okay. So it's not like friction is a force comes out of something. Friction is just like saying, well, look, I'm going to put let's say if I put little tiny bowling pins on the surface, you could understand that, okay, now if I drop it and it can hit the tops of these bowling pins, that what it's going to do is it's going to give its momentum to the pins. So for the pins to move, they're going to get a little vector. So each time a pin moves, it's a little vector. It's a little vector of energy, mass times velocity, mv. All right, and this is going to lose that mv when this gains it. That's the equal and opposite reaction. But this isn't a force. You don't say the pins apply a force against the bowling ball. They're not doing anything. They're taking energy. They're taking a portion of the thing's energy. So the thing starts off with energy, and all friction is friction is just leaking out. Friction is just you giving pieces of that away, okay, with interaction. Your line gets shorter and shorter. Oh, shit. I do have to remember. Now I'm in trouble. Yeah, now I've screwed it all up. I do have to remember to see what's in the camera's view. I have to draw a reference, and then I'll know. But anyway, the simple point is the friction is just the surface, the contact, and you're just saying how much of the energy, how much vibrations, how much motion, mass moving, how much mv have I put into the surface, and whatever I put into the surface, I took out of this object. So you're just changing the direction of your vectors, if you want to look at it that way. But fundamentally, you're just sucking the energy out of something. So there's no force of friction. Friction is just you finding a way to pop something's balloon, to poke a hole in it and let the air out. You're just taking the energy and making it go somewhere else in a smaller and smaller things. But it's not a force. Shouldn't even be implied to be a force, because it's like, again, it's like calling time a dimension. It doesn't fit the rules. Friction doesn't fit the rules of being a force. It's a sink. It's a place energy can be pulled out of something.
We will need to be able to do certain operations with vectors in order to perform our calculations. So let's learn how to do simple vector operations.
So he didn't really do the vector scalar thing in much of a, so that's the title of the video, and he didn't really go into it. So this is just adding vectors. So this is just understanding that if you have motion in this direction, you have motion in this direction, you'll end up traveling this direction, in a hypotenuse. Okay. And so you won't be going, you can't add these two directions and say those two directions are a straight line, and now I'm going, say if I'm going 5 miles this way and 10 miles this way, that somehow, okay, I'm going 15 miles an hour. Well, no, I'm going something like 12.
If we want to add two vectors together, it's pretty simple. We just make the second vector start where the first vector ends, and then create a new resultant vector that goes from the start of the first to the end of the second.
And that's just because that's physically what happens. So I'm just saying, yeah, so you're just duplicating what physically actually happens with the Newton's ball. You throw it off a cliff, gravity's going this way, this is going this way. The two forces, the two momentums, don't have anything to do with each other, really. They don't interfere with each other, and you end up with a result that hits the ground with more energy because it has two components.
In lining up two vectors, we have to make sure they retain their direction, as that is important information. If the vectors point in the same direction, their sum will just be a longer vector, and the magnitude of this resultant vector will simply be the sum of the magnitudes of the original vectors.
Right, so if you take a 5 mass going 10 v, and you add a 0 vector to it, but a mass, and make a 10 mass going now 5v, you lose half your arrow, but you have to spread over twice as much mass. So you can just understand, mass is the bread, and you can spread velocity on it. So if you have twice the surface area of bread, then you have half the velocity thickness. You know, it works that well, and somehow they need to break that rational physics and believe this Leibnizian crap.
So in this case, 4 plus 3 equals 7. Sometimes there is an angle between the two vectors, like these perpendicular vectors. In this case, when we draw the resultant vector, it will be the hypotenuse of a right triangle. The
It's always going to be a hypotenuse, but whatever.
magnitude of this resultant vector is not the sum of the other two magnitudes. This one can be found by using the Pythagorean theorem, which we may remember from algebra class. A squared plus b squared equals c squared. Plug in a and b.
Or you could just measure it. But yes, that formula does work. Yeah, the 3, 4, 5. This is the, the perfect example one. Where you have nice round numbers.
Square them and find the sum. And then we take the square root to get c, which in this case will be 5. When we are
But in most other cases, it'll be some sort of 5 point or 7 point
looking at right triangles, we can also use trigonometric functions to find the unknown angles. All we need to do is choose an angle, which we represent with the Greek letter theta, and label the sides of the triangle as opposite, the leg directly opposite the angle, adjacent, the leg right next to the angle, and the hypotenuse, which is always the longest side. We can use the lengths of these sides to find the sine, cosine, and tangent of this angle.
Right. So there's two ways to do it, and I would just, I'd argue that sticking with the more Pythagorean one of the, the vectors rather than the angles, it's a lot more coherent.
We will cover these functions in more depth in the upcoming mathematics course. But for now, all we need to remember is the mnemonic device SOHCAHTOA. Sine theta is equal to opposite over...
Why the fuck something would do this? Jesus. Oh, God. Like everybody's going to be able to... Oh, it's SOHCAHTOA. Oh, okay. Yeah, I know how to spell that.
Hypotenuse. In this case, that would be 3/5. Cosine theta is equal to adjacent over hypotenuse, which here will be 4/5. And tangent theta is opposite over adjacent, or 3/4. To solve for theta, we can use any of these equations. Using this one, we can take the inverse sine of both sides. That makes theta equal to the inverse sine of 3/5. Just put 3 over 5, or 0.6, into your calculator and press the inverse sine button, which may look like any of these expressions.
So this is hardly the ideal. I guess there are circumstances where you only know the angle and you don't know the exact dimensions of the triangle.
And we get about 36.9 degrees. Trigonometric functions like these relate the angles of a right triangle to the lengths of the sides, and we will use them a lot in physics. But it usually won't be more complicated than this, so don't worry too much about it. Also, if you are using a graphing calculator, take a moment to familiarize yourself with the different settings it uses to report angles, which are degrees and radians. If you are more familiar with degrees, make sure that setting is selected, and we will learn about radians another day.
So whatever that is, shoved in the middle of this video.
Hey friends!
That's it? Well, that was pretty suck. It can't be the whole video, right? No, I'll pause and see. Alright, just a commercial. So he says, now that we understand vector addition, let's go through a few
other operations. Vector subtraction will be similar to vector addition, except that when subtracting vectors, we will again line them up head to tail. But we will invert the direction of the second vector. This is the same as multiplying the vector by a scalar of -1. This way, the magnitude of the vector remains the same, but its direction is reversed. So instead of a plus b, which looks like this, a minus b would look like this, which is essentially a plus -b.
Right, so the negative part makes it a little bit easier to understand. But fine, yes.
We find the resultant vector, and that's all there is to it. Another thing we might want to do is break up a vector into x and y components. This is
You already did that, basically. But anyway, continuing.
useful when looking at projectile motion. If a ball is thrown at an angle, its velocity can be represented with a vector. But because gravity is operating on the ball in the y direction, pulling it down to the earth, we will want to be able to separate its vertical motion from its horizontal motion.
So you could just break it into a bunch of little triangles. And that's basically what calculus is.
So we can take this vector and split it up into components. All we need to know is the magnitude of the vector and its angle from the horizontal. Then we can use trigonometry to find the lengths of the legs of a hypothetical right triangle. Sine of theta gives us opposite over hypotenuse, and cosine theta gives us adjacent over hypotenuse. On both of these, we can evaluate the trig function and multiply both sides by the hypotenuse, which is the value we know, to get the legs of the triangle, which will be the x and y components of the vector. We will see this in more detail later. Vectors can also be multiplied by scalars or other vectors. When multiplying a vector by a scalar, we will simply multiply the magnitude of that vector by the scalar, while keeping the direction the same. So if multiplying this vector by 2, its length will double. Two vectors can also be multiplied, but that will be more complicated, so we will go over that another time.
And why would you multiply vectors? I have to think about what circumstance. Yeah, I can't think of any.
Let's try one example to make sure we can do these kinds of calculations. Say you are in a boat traveling across a river, and the boat typically moves at 4 meters per second in still water. But the current is pushing you downstream at a rate of 1 meter per second.
All right, so he has a boat that has obviously a motor because it's going 4 meters per second. So I don't know, yeah, it's kind of bullshit, right? Or wind, something's moving it, and you're just saying there's some other force you're going to apply to take away that. So obviously the net is going to be 3 meters per second. This one's a little too simple, but...
What is the speed and direction of the boat?
Speed and direction. So why is he using the word speed?
To answer this and almost any other problem we study in physics, it is best to draw a diagram first.
Right, you don't have any direction except opposite.
Here's a top-down view of the river and the boat.
So the river could be understood as gravity. It's the same exact thing, frankly. And, well, I mean, it's the same exact thing when it's accelerating you, right? Once you're at the peak speed of the same speed as the river, well, then it's not going to be the same anymore. It's not a good analogy.
Draw a vector that is horizontal with a magnitude of 4. We then need another vector to represent the current. That will point straight down and have a magnitude of 1. To find out the speed and direction of the boat.
So that doesn't make much sense. I mean, he's saying there's a force with, why would it be straight down? So, yeah, the current's not going to be anything other than just a opposite direction. He just pointed out the current's in the opposite direction. So what the fuck are you talking about? The current isn't down.
We have to add these vectors together. In order to do this, we can move the vector that represents the current over here, so that we are adding head to tail, and then find the resultant vector. Or we could have left it where it was, made a rectangle using the two vectors, and then just drawn the diagonal. Either way...
So this is another case where they just make up something and this isn't a real experiment. Does this make any sense? Sorry, I can't make any sense out of it. The current's going opposite the direction of the boat. It's just the current's just as equal a force as the force pushing you, presumably. You didn't say the wind is more powerful than the current in terms of displacing or pushing the boat. So, yeah, it doesn't mean much.
This vector sum will have a magnitude of root 17. To find the angle from the horizontal, we can use any trig function we like. Say we use tangent. Tangent theta will be opposite over adjacent, or 1/4. Taking the inverse tangent, theta must be 14 degrees. So the boat is moving at a speed of root 17 meters per second in the direction of 14 degrees off the horizontal.
So none of that makes any sense from what he described this as far as I was concerned. I mean, that's not the thought experiment he described, is it? The boat moves 4 meters per second, but the current is 1 meter per second. And what direction? Let's try it again. Sorry, I couldn't make any sense out of that.
Vector by a scalar, we will simply multiply the magnitude of that vector by the scalar, while keeping the direction the same. So if multiplying this vector by 2, its length will double. Two vectors can also be multiplied, but that will be more complicated, so we will go over that another time.
So again, square velocities. Yeah, no, I don't think so.
Try one example to make sure we can do these kinds of calculations. Say you are in a boat traveling across a river, and the...
Okay, so you're going across the river. Okay, so that's the catch. You're going across the river, and you were launched at some speed, and there's no friction or something. How do you he doesn't describe how you're going 4 meters per second across the river. So is it a wind?
Boat typically moves at 4 meters per second in still water, but the current is pushing you downstream at a rate of 1 meter per second.
Okay, so that's why the tangential line. So you're going across a river, and the current's this way, and so it's going to move you. So that was okay. But yes.
If you're taking anatomy and physiology for the first time, I can guarantee it's not like any course that you've ever taken. And that's why so many students struggle with it. But what if I told you there's a secret study tool out there that you could use to help you ace your next anatomy exam? It's called Anatomy.
All right, should be back. Technical issues. Let me just try something. Well, that didn't work. Anyway, so all right, let's just play this a little bit and then I'll explain.
Tangent. Tangent theta will be opposite over adjacent, or 1/4. Taking the inverse tangent, theta must be 14 degrees. So the boat is moving at a speed of root 17 meters per second in the direction of 14 degrees off the horizontal.
Right, and he could have just, done that square root of 17 thing and just turned it into a real number that would have been, somewhere between 1 and 3. But anyway, well, it'd be 3 plus extra. All right, so that's the whole idea, that you can add velocity by adding a tangential perpendicular motion. So you could throw a baseball off a train, and it'll have a combined velocity of the two motions, but you can't add them. So that's relevant to another part of what they argue to be reality. So I might as well get to that. Which is you can't do that with photons. And the minus velocity part is also kind of interesting. Well, I can do it with the light argument, but it's better to do it with the orbiting argument. So as I pointed out, when something's orbiting, its velocity is actually changing. So as it's orbiting, it's got its vector this way, and it's going to get pushed straight down. So you could argue, okay, that it's gained velocity because it's going to travel this kind of a line. And and in each case, the perpendicular off the surface is doing that. And what you can understand is the next perpendicular line, okay, actually is going to have a component, okay, in this direction. So even though it's going this way coming in, it's going to have a component that's going to have a portion against its own velocity. So this arrow will have a little portion from the gravitational force that's actually against it. All right, so you're going to end up with a reduction in the velocity. So it's basically just oscillating between giving it extra velocity and then taking that extra velocity away with the next bit of gravity. So, you gain a little, you lose a little, because your angles keep changing and keep absorbing whatever increases in velocity you end up with. If you were just falling, you can understand that you just keep gaining more and more force. So you're falling, you're getting the longer line vector, but the gravity is up against it as you keep changing the angle. So when you're on the opposite side of the Earth, you're actually falling in the opposite direction. So it's completely annihilating everything you gained theoretically from the other side of the Earth. It all works out. But anyway, let's just do that stupid train thing. So you're on a train going 9 miles an hour this way, and you throw a baseball 90 miles an hour this way. All right, so you have two vectors. I could say this line and then this line. And the baseball is going to travel the combination of those two, right? So I just put this line here, and I can draw my new vector, my hypotenuse. And so this is just going to be, larger than this 90. So you could say it could be 110. All right. And so your baseball is actually going to hit the ground with this velocity times its mass, so it will have more force than if you just had the train's motion, or if you just had the throwing it perpendicularly off the train's motion. It's going to have more capacity to impact because you've increased technically the baseball's velocity. Its absolute velocity, its net velocity, let's just say, is a higher number. Now you can't do that with light. So the famous argument is that somehow there's photons can be bent, and the argument is that photons, I would argue, are one-dimensional objects. They can't carry more than one velocity. You can't do this trick to a one-dimensional object, where you say it has two distinctly different velocities. It has this way, and it has this way, and it can have that way. So with the light clock example inside a spaceship, if I shoot a photon, the photon never leaves with this velocity of the spaceship. Okay, so when I emit the photon's not going, okay, I'm going to shoot it this way, a laser beam. The laser beam isn't traveling this way with the ship. It can't have both velocities. It's only going one way. So the photon is one-dimensional. So it can never be bent in the sense that you can't apply a force to its path, cause it to travel some other trajectory, and then get to the side at the same time. It has to get to this side. It hits this side at the same time. You can't change when it hits the other side of the spaceship. So you can't have more distance traveled without an increase in its velocity. And you can't change the speed of the photon. So the simple argument is that, yeah, photons won't do that. And so this is all based on the fact that they think we should expect things to, how they look is how they are, when we know it's not about how they look. So if you had two lighthouses, one close to you and one very far from you, you would look at the two, okay? And this one would look big and this one would look small. And you'd say they're not the same. One of them's a tiny little lighthouse and one's a great big lighthouse, and that's how they look. But, the physics knows, no, that's just an appearance. These are actually exactly the same. This one's the same as this one. And so they're sort of expecting that the reality is that what you're supposed to do is supposed to build a little tiny lighthouse that's close, and then a really big one that's far away, and then they look the same, and now they are the same. So they say when it looks the same, it is the same, and when it's, and when it looks different, then they're not the same. So we know that when it looks different, they are the same, and we know it's exactly the opposite. Because, we're smart enough to know it's not about how it looks. It's about how it is. And you can get into arguments about simultaneous events and some kind of idea that there's any place you can sit in the universe and change the fact that it was simultaneous. You can't change the fact that two events happen at the same time by changing your perspective. So what you see isn't what is. And that's physics. Physics is understanding perspective. Perspective breaks reality. Okay, it creates illusions and delusions. It distorts the truth, but you can understand every one of those distortions, so they shouldn't get in your way. But that's what physics is doing. Physics is saying what you see is the reality. And that's what the equivalency principle is arguing. That somehow it doesn't matter how the event happens, it just matters that if it looks the same, it is the same, and it's not the truth. The gravitational force moves your entire body, atom by atom. So the floor of an elevator moves your feet, okay, and then your feet move your legs, and then your legs move the rest of you, okay, and that's the truth, is that it's not the same at all. The force moving you one way in gravity, you can't feel it, you can't know it's happening, because it moves every one of your molecules and your atoms and your electrons and protons. It moves them all at the same time, at the same speed, so you can't feel it, but certainly you can feel the floor of an elevator. So they're not the same. Alright, enough of the video, I think. So, sorry about the technical issues. I think this new drawing thing works better. It looks better anyway. So I'll probably stick with that for a while. Until I do something else. But anyway. Yeah, I think that'll do. So, I'll continue doing this. And playing these videos. I think this is all he's doing here. So I should finish his video. But I think it's already finished, frankly.
It may seem abstract right now, but we will be using this sort of approach in order to understand motion in almost any situation you can imagine, because it's just about using vectors.
So all forces will be represented by vectors. So is kinetic energy a force then? What is kinetic energy? How does it relate to a force? So, it's all, and again, MV works as long as you understand that, yes, photons have a mass, and they have the velocity of the speed of light, and they convey a quantum of energy, defined by Planck. So, what's the complication? There isn't any. And they had to just ruin it all by squaring velocities.
To represent the forces acting.
Again, their physics says it takes 25 times the fuel to move something 5 times as fast. And that something going 5 times faster will do 25 times the impact damage. That's what their physics asserts. And it clearly doesn't happen in reality.
On any object. Now we are ready to move on to the physics. But first, let's check comprehension.
Oh, I hate this shit. Fuck you in the ass until fucking dead. You fucking Weasley cunt bastard. With your little fucking I know more than you. Can you pick which one of these stupid things is correct? Fuck you, little quiz master. Shove it up your ass until you are really, really septic and dead. You dumb fucking piece of shit.
Thanks for watching, guys. Subscribe to my channel for more tutorials.
Oh, fuck you. Tutorials. They're tutorializing. Tutorial, just another word for molestation of neurons. Okay, I will never do a tutorial. Yeah. It's like some sort of butt scope. Anyway, till the next time and such and so forth and whatnot. God, I hate this planet. Unsubscribe from Earth. If at all possible.